So I just took a drink out of a glass. Apparently, it wasn't clean because the first thing that went into my mouth were like small pieces of food debris that didn't get cleaned off in the dishwasher. That was pretty gross way to start enjoying a beverage. But hopefully there are no more and life will go on. Wow, it's been a long time since we've done a video. Just finished winter break and now we are starting our unit on trigonometry. Now my roommate is cooking some meatballs and spaghetti, so I will be interrupted shortly to attend to that. But until then, let's start talking. Goal for this video is to understand the fundamental basic ideas of what trigonometry is, what it means, and how we're going to start using it. So we're going to talk about a lot of different vocabulary that we'll reference throughout the unit. We're going to look at a few formulas, some geometric formulas, and we're going to talk about different ways to measure angles. Quick question, what is trigonometry? Trig, oh, right there, that's kind of like triangle, and nometry is kind of like measuring things. I know that's not a complete connection right there. Trigo is like you're like, okay, I see the triangle, kinda, I'll buy it. But then nometry, measuring, I don't know. Well, that's because it's all Greek. But it is referring to the measurement of triangles. So specifically comparing the angles and often referred to as theta. That was a theta. That's not very good. That's essentially the same and still not very good. I don't know, whatever. Apparently I can't draw thetas very well. Maybe they're more ovular like that. No, maybe they're squigglier. I don't know. These just look like, I don't know, some sort of like poorly decorated Easter eggs or something like that. Anyways, I digress. But trigonometry, measurement of triangles, it was initially totally concerned with comparing ratios of sides and angles, and was very useful in the early days. And it was used for calculating astronomical things, used for navigating on ships and stuff like that, used for surveying, so like looking at land and figuring out elevation and all that, and building. They could use properties of triangles to build sound structures, which is pretty cool. But it was all based on this idea of the triangle. And then a little later down on the road, they decided to think of it not only as these relationships within triangles, but actually as a function of an input, often written as t for theta, but that could be confusing because we sometimes think of f of t as t being time. So you'll see things like f of theta as well. But we're seeing these as functions, as trig functions. You probably know they look something like that. And my dog's scratching at the door, so hold up. Alright, she's curled up in the bed. She's looking super cute, so we can continue. So we're going to briefly run through some terminology that we're going to want to be familiar with for our introduction to trigonometry. First off, an angle drawn in standard position is going to have its initial side. It's going to lie on the positive x-axis right there, and then the angle will open up to whatever theta value that angle happens to be. In terms of rotating a ray over to the terminal side. So that's kind of technical. You don't really need to worry too much about that, but important to know the terminology. But you should know standard position will always start like that, always with that positive x-axis right there. All right, so if you measure an angle positively, then it's going to move counterclockwise, which may seem counterintuitive, but if you have a negative angle, it's going to move clockwise. So maybe this is, if we're thinking about degrees, I don't know, maybe this is like 135 degrees or something like that, and maybe this angle right here is like negative 45 degrees because it's moving clockwise. Another important term to know are coterminal angles. Think about that picture we just saw right here. The terminal side is essentially where your angle finishes, and so coterminal angles share an initial side and a terminal side. And if you think about what we have here, if you were to add coterminal angles together, what would they equal? Well, whatever that circular thingy right there equals, which we'll talk about in a moment. So, how many degrees are in this angle? Well, that is a right angle, which means that is a 90-degree angle. Okay, that's not too fancy right there. I could draw a triangle, and now I have a right triangle, and that's kind of cool. Or I could put two of those angles next to each other, and think of it as one angle, and then I would have to say that I have two right angles, each 90 degrees, so a total of 180 degrees. And then I could put two of these together and say that I have 360 degrees. And if you think about it, this is making one complete revolution. Sorry, I'm kind of like sick and mucusy, so I'm coughing and phlegming. It's gross. So then, how many degrees are there in this red shape? Well, this red shape is a circle, which is going to have 360 degrees of revolution. So again, seeing those four right angles right in there, kind of making up that circle. And so now let's think about this shape, which is a rectangle. A rectangle. Whoa, I've never thought about that before. That's kind of weird. But it's four right angles, so this also is going to have 360 degrees for its interior angles. And now compare that to this triangle, which is, if you picture it, it's half of a rectangle. And so it will have half of the degrees that a rectangle has, and so the sum of the interior angles of a triangle will be 180 degrees. 180 there, 180 there, making a total of 360. My desk is really squeaky. Can you guys hear that? All right, so pretty good talking about angles measured in degrees, but what about radians? First off, what on earth is a radian? Well, think about what that word radian sounds like. It kind of sounds like the word radius, which if you remember, if you have a circle and you take a line from the center of the circle and it goes out straight to the edge of the circle where it lies on the circumference of the circle, that is a radius. Wow, that's an R. And you can also think of it as half of the diameter of a circle, whatever you want to think. So half the diameter equals the radius. Diameter being the largest chord of a circle, chord being a line that goes through two sides of a circle. So that right there, between those 2 points, would be the largest chord, which is the diameter, which is twice the radius. So saying a lot of things, but okay, what does that have to do with angle measures? Well, it's pretty cool. We have this definition. 1 radian is the measure of a central angle. Central angle just being this angle right here that is created by these two segments right there. Notice that this central angle intercepts an arc, which is just saying a portion of that edge of the circle. We're denoting that the length of that arc as S, and what we're claiming is that the definition of a radian is the value of the central angle that gives you an arc length of the length of 1 radius. So if you think about this radius right there, if this were not a straight line like that, imagine if it weren't a ruler, but rather, say, a soft tape measure, and you could curve it and bend it, but it still had that same length. What we're saying is take that and lie it on the edge of your circle, and however far it goes, connect the endpoints to create the central angle. That angle right there is 1 radian, and we can use that to figure out some pretty cool things, which we're obviously about to do. So think about what we know from geometry. We know that the circumference of a circle is equal to 2 times pi times the radius, or another way of saying that is the diameter times pi, because 2r is the same as a diameter. But it's more useful for us to talk about it in terms of the radius. I have to burp, I'm sorry. Okay. So, we want to know then how many radians are in a complete revolution. Well, think about what we know. We're taking the circumference of this circle, c equals 2 pi r. We're taking this circumference right there, and we're splitting it up into these sections of different, essentially, radii lengths along the circumference. So you can continue along like that and continue to add more and more of these lengths of radius in there. And eventually you're going to get back around closer and closer. Sorry, this is kind of awkward. And you're going to end just shy of, well, just over 6 of those. 1, 2, 3, 4, 5, 6. Because think about what we're doing. We're literally splitting up the entire circumference, which is 2 pi r, into sections of length radius. And what mathematically are we talking about when we say we're going to split it up into those different pieces, and how many are there? Well, we're talking about division. So we need to take 2 pi r and divide it by the thing we're splitting it up to, which is r, because the length of a radian, the length of the arc of an angle that creates a radian is the radius. And so notice we have a r and an r canceling out, so we're left with 2 pi. So in one full revolution, there are 2 pi radians. That's pretty cool, and this is what I was drawing there. Notice that 3 radians is almost 180 degrees. It's a little shy, and so then similarly, 6 radians is just a little bit more shy than 1 full revolution. And what's the connection there between what we just said, 6 radians? Well, we said that there are 2 pi radians in a full revolution, and 2 pi, if you think about pi is 3.14159. We're multiplying it by 2. So we're going to get roughly 6.282. And so we have that little extra 2.82 length right there, but it's pretty close, and it is exactly 2 pi radians. And if you think about what that is in degrees, we know it's 360 degrees. That will come in useful in a little bit. So let's think about this. We know that the measure of an angle, or we're told that the measure of this angle, ACB, so this angle right here, we're told that is 90 degrees. So we know that is a right angle. And we know, furthermore, that the circumference is equal to 4 units, whatever they are. And we want to know, what is the length of this arc right there? Well, think about it. If this is 90 degrees, then we've essentially just split the circle up into 4 equal sections. So each of these arcs are going to be equal in length. And there's 4 total, so it's got to be 1, 1, 1, and 1 to make that total of 4, giving us 4 right angles right there. Okay, that's pretty cool, but what if we're dealing with something that's not such a pretty number? Well, think of another way we can do this. Ready? I think meatballs are ready. We'll find out shortly. I'll finish this thought. So think about what we're doing. We're saying that this arc length is going to be some percentage, some fraction of the whole circumference is going to equal that arc length S. And what's nice is that it's going to be whatever fraction this central angle happens to be. So in our case, we knew that that central angle was 1/4 of the total thing. More specifically, we knew that it was 90/360ths of that total circumference, so we can multiply it by that circumference to get S. But 90 over 360 will reduce to 1/4, so we get 1/4 times 4 equals S, which gives us 1, and the same answer we got there. So, again, generalizing it, and now let's generalize it in terms of radians. We know that the arc length S is going to equal the total circumference of the circle times the fraction of the whole circle of that central angle. So if we're talking in degrees, then it's going to be the value, that's bad, the value of that angle theta divided by 360. Or if we're talking about radians, it's going to be the circumference times the value of that angle in radians divided by 2 pi. And let's look at what happens when we use the radian measure. It's pretty nice because we know that an equivalent way to write the circumference of a circle is by writing 2 pi r. And we are multiplying this by the theta value divided by 2 pi. Well, extend that right there to help you visualize this. Notice we have a 2 pi and a 2 pi, so we're just left with that, r theta. And so S equals r times theta. What is that saying? That's saying that the arc length S will equal the radius times the central angle in radians. And that's cool because that's like a really easy formula right there. Radius times theta. That's pretty cool. And manipulate it a little way, you can also get this related identity there, that the arc length divided by the radius will give you the value of that central angle. You'll have to use that later. But I'm going to go check on these meatballs. Oh my gosh, I'm so full. Ate 2 bowls that looked like that. So delicious. You have no idea. But I guess we'll do some more math, some more things to know and to talk about. So first off, the 4 quadrants of our familiar coordinate axes. We got quadrant 1, 2, 3, and 4 right there. Again, notice starting in the positive quadrant and then working counterclockwise from there. Now in terms of angles, notice they have them listed here. 0 right there, and then as you move up, 90 degrees up is equivalent to pi over 2. 180 degrees over is equivalent to pi. 270 degrees all the way around like that is 3 pi over 2. And a full revolution back to 0 is equivalent to 2 pi radians. And so you can think of it in terms of degrees or radians. It's going to work the same way. But for what we're doing in this unit, we're going to be focused primarily on radians. Real quick, acute angles and obtuse angles. An acute angle is an angle that is between 0 and 90 degrees, or equivalently 0 and pi over 2 radians. So something in this first quadrant right there. That would be an acute angle versus an obtuse angle, which is going to be between 90 and 180 degrees, or between pi over 2 and pi radians. So an acute angle like this in standard position will lie in quadrant 1, and an obtuse angle will lie in quadrant 2 with its terminal side. Do you remember what complementary and supplementary mean? Well, complementary means it's referring to 2 angles that add up to 90 degrees. So if you have a right angle and you split it up into 2 angles that you want, those 2 angles are complementary. Angle A and B are complementary. If you're talking about radians, then it's 2 angles that add up to pi over 2. Compare that to supplementary, which is going to form a straight line, a straight angle. So these will be any 2 angles that forms a linear pair. Means when you add them together, you get 180 degrees, or equivalent, you get pi radians. So that's what we have going on right there. And finally, let's think about this. How do you convert between radians and degrees? Well, let's think about what we know. We know that 1 full revolution is 360 degrees, which is equivalent to 2 pi radians. But that's a little redundant because we have extra factors of 2 in there. So I could simplify that to 180 degrees is equivalent to pi radians. And we can use this as a conversion factor, just like we know that 12 feet is equal to, well, that's not how I meant to do that. Let's say 1 foot is equivalent to 12 inches. And in the same way that if we knew we had, say, let's say we knew we had 36 inches, and we wanted to know how many feet that was, we can multiply this by the ratio. Notice inches are right there in the numerator, so we want inches down here, which is 12 inches per 1 foot would be our conversion factor. Well, it's going to be the same exact thing here for converting between radians and degrees. If I have an angle that is, say, 3 pi over 4 radians, then I need to multiply this by my degrees divided by my radians. And my degrees are 180, and my radians are pi. And so when I multiply this together, notice I have a pi and a pi that cancel. So I have 3 times 180, which is 540, divided by 4. And my units are no longer radians, but now they are degrees. I don't know what 540 divided by 4 is. Wait, 40 divided by 4 is 10, and 500 divided by 4 is what, 125? So 135 degrees is equivalent to 3 pi over 4 radians. Another way to think about that is picture the unit circle. We know that we have 1 pi over 2, 2 pi over 2, 3 pi over 2. So we're talking about 200. I'm making goofs because it's been so long since I've done anything. We're talking about pi over 4. So pi over 4 are going to be our 45 degree hungamungas. So we're going to have 45 degrees plus 45 degrees is 90 plus another 45 degrees is 135. So we got there the same way, just thinking about it a little bit. 135 degrees there. But what if we wanted to go the other way? Say we know a degree measure. Say we have 30 degrees, and we want to convert that into radians. Well, we need to multiply that by pi radians divided by 180 degrees. And when you do that, it will simplify down to 30 over 180 is the same as 1 over 6. So we get pi over 6 radians is equivalent to 30 degrees, and that might sound familiar to you. It probably does. Last little bit of thing we're going to talk about here is linear and angular speed. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed of the particle is the arc length divided by the time. So what it's saying is picture a little like cylinder here that is maybe rotating along. Let's say it's rotating along like that, counterclockwise. What it's saying is picture, cool way to think about this. Imagine you're rolling paint out. If you're rolling paint out, then the paint that gets laid onto the surface is going to be that bottom layer right there as you roll forward. And that's going to move as you roll it this way, like that. This particle is going to move like that. So it's going to rotate, and it's going to correlate to some, bit of paint that's been laid down. And that length right there, divided by the time, would be the linear speed, because it's putting it out in a linear path like that. So what does that mean? Well, figure out what that arc length right there is, and divided by the time, that's your rate. Distance divided by time, that's always how we do a rate. Well, here's a slightly different rate. We can talk about the angular speed, which is essentially talking about the rotational speed like that. How quickly is it rotating? How many revolutions in a minute, or something like that? Well, that's going to be whatever that angle is, whatever fraction of the whole it has rotated, divided by the time it took to rotate that much. So if a lawn roller with a 10-inch radius, so same exact idea as what we just drew here, so I'm going to draw a new one. We've got this radius is 10. Okay, I need to draw that bigger. Okay, how about this right there? Radius is 10. It's a lawn roller, so it's going out like that. I'm not the best artist in the world, but that's okay. We will all survive. We've got this lawn roller, 10-inch radius, makes 1.2 revolutions per second. And we want to find the angular speed of the roller in radians per second. Well, to figure out the angular speed, we need to figure out what that central angle is. Well, we know that it is doing 1.2 revolutions, and so that central angle is going to be 1.2, 120% of a full revolution. So we know that a full revolution is going to be 2 pi, so this is going to be 120% of 2 pi, or more simply put, 1.2 times 2 is 2.4 pi radians per second. And if we then wanted to know the speed of the tractor that is pulling the roller, I guess there's some tractor here pulling it. That is a tractor. Take my word for it. And we want to know what the speed of that is. Well, that's going to correlate to the linear speed. How quickly is that thing rolling along the ground? And so to figure that out, we need to figure out the arc length, which is similarly going to be 120% of a full revolution. And we need to take that and divide it by the time. And so what we're dealing with then is going to be the arc length is going to be the circumference, which is 2 times pi times the radius, which is 10, and it's going to be that multiplied by the angle. And what is the angle, you might say? Well, the angle is going to be 120% of 2 pi. I don't know what I just said a moment ago, but I think I misspoke. So let's start this problem from the beginning. Find the speed of the tractor that's pulling the roller. So we know that it is going to travel a 120% of a full revolution in 1 second. And a full revolution is going to be the circumference of this, which is, again, 2 pi r. So 2 times pi times the radius, which is 10. And this is going to be 120% of that, so times a 1.2. So notice, actually, we have a similar situation here before. We had the 1.2 times 2. We had a 2 times a 1.2. So we have actually a 2.4 times pi times 10, which I'm going to write as 24 pi. And you can calculate that and figure out what it is. Keep in mind this is over 1 second. 1 second. So 24 pi inches in 1 second. I guess we should include units here. 24 pi inches in 1 second. Multiply that out by pi, you're going to get roughly 75.4 inches per second. Done.